American Meteorological Society's policy program is supported, in part, by a public-private partnership.
What we'll do in the future is we'll have a system that tells us what's the likelihood that flash started a fire, and it'll use the NLDN or the ENTLN or any of these ground-based networks to tell you where the flash hit, and it'll use the satellite to tell you how long that flash lasted.
So our next speaker will be Dr. Rudlosky. He's an adjunct assistant professor in the Department of Atmospheric and Oceanic Science at the University of Maryland, College Park. He also works as a physical scientist co-located with the Cooperative Institute for Climate and Satellites, Maryland, and he serves as a member of the GOESR Risk Reduction Team. Dr. Rudlosky.
It's kind of exciting that we have the three of us together here because we really represent three different aspects of the field, and we all have kind of a different focus. And if you're able to see the slides, on the title slide in the lower corner, I have two logos, KICS Maryland and ESSEC. And that's where I sit, up at the University of Maryland. It's a great place. I sit at a triple point between academia, the federal government, and the private industry. And so it's a really neat place there, and we get to do a lot of neat research. So we have a lot of students working with us as well. So on to the next slide, I have an outline and overview slide, and Amitabh has already shown one of the pictures, the types of lightning. But in the top right picture, we're just focusing on the smallest little third of that where the weather actually happens. We're not focusing on the sprites and the stuff that happens higher up. Since Amitabh already introduced a lot of the lightning observations, I'll breeze through that fairly quickly. The next section is storm warning applications, and normally I would expand on that at great length, but I'm just going to highlight a couple of those examples, and really my focus is going to be on the public safety applications, and so that's what most of my talk today. I just went to try to advance the slide, but I just have to look at the next one on my paper here. So if we do go to the next slide, we have lightning observation networks, and again, Amitabh covered a lot of this, and so we have both the regional networks and the global networks, and I put those in quotes because they're limitations to both. So the first set, we say regional, so he talked about the NLDN, that's the whole continental wide. The plot that I have there, that shows the locations of the lightning mapping arrays with a 200-kilometer radius drawn around them. That's where we get detailed observations with the VHF, the very high frequency. And now if you look to the right, there's a picture there with the pretty colors. That's a cross-section through a storm, and the colors are radar. And so what you're seeing is an updraft there, and circled on the bottom is a little minus sign. It's very hard to see, but it's just one point. That's the thing to say. So the NLDN tells you lightning struck that point. If you look above that, there's all those little white dots that are in the updraft. That's what the lightning mapping array sees. It sees the 3D channels. It sees everything that's in the cloud, but it won't see where it comes to ground. So you have to combine the two networks to understand, to see the whole process. As opposed to that, he mentioned the global networks. We have both ground-based and satellite-based. The one image I really want to draw your attention to is the middle one with the globe. What that shows is NASA's Tropical Rainfall Measurement Mission, which has the lightning imaging sensor. It's been very consistent since its launch in '98, so we use that actually as validation. That's my main research, actually. But what it shows is it's a swath. As it flies over, it sees the ground for 90 seconds at a time. And so if you're looking at an evolution of a storm, that's not going to provide that much information. You can only see a snapshot. And so you need a longer period of time. The bottom right image, that shows you the pixels. Amitabh was talking about the pixels. So each of those blue pixels, there's lightning in it. And the little white dots, that's the LMA. So you can see the LMA is smaller and that light is more diffuse at the top of the storm. So you have a larger area that this. So it just shows these different types of data sets see, as Amitabh covered very well, they see different aspects of a lightning flash and are therefore very complementary to one another. And so if you go on to the next slide, on the top it says ground-based lightning network performance. This is my main research, and this slide's a little bit old. I have a new paper that I am hoping will be accepted formally in a week here or so. But basically what I've done is I've used the satellite, the lightning imaging sensor, and I've said, okay, within its swath, it sees everything. What fraction of everything does the ground-based network see? And so what you see in the colors there on the map on the bottom, anything that's red is over 25%. And so it could be 50%, it could be 60%, but a baseline is 25%. And so that's a large area, and this is 2012 and a fairly new network. The GLD 360 is more developed now, so I would imagine this would look a little different at this point. In the tables there, I just show the detection efficiency is around 25%. The one thing, the location difference is 12 kilometers, and so that's really interesting. I just showed you the map where the footprint of the Liz is a lot bigger, but the center that Liz sees and the center that the ground-based network sees are fairly close, and that's very encouraging for when we do merge these data sets in the future. But the one point I wanted to make with that is you can see it's not consistent. It varies. The detection efficiency is completely dependent, or very highly dependent on how many sensors you have and where your sensors are. So if you have more sensors, you'll have better detection efficiency in general. In some remote regions, such as out west, you can see there's a discontinuity there. The mountains get in the way. It's harder to deploy sensors there. There's fewer sensors, less detection efficiency. Out over the oceans for a similar reason. There's just nowhere to put sensors. And so that's going to the very next slide. The GOESR Geostationary LightningMapper, that's one of its main advantages, is that it'll be uniform in space and time. From almost Japan all the way to Africa. We're going to have, with 2 sensors, we're going to have that whole area covered at about 8 by 8 kilometer resolution. And so what I've shown on there is that it'll observe both intracloud and cloud to ground lightning, and that's very important because the first flash is almost always intracloud, so you want to catch it early. But it's provided, the GLM will provide data at spatial and temporal resolutions that we currently don't have. So what we're doing is we're using these existing ground-based networks to mimic what we'll have in the future. And this is all part of what's called the GOESR risk reduction plan. We want to make sure that as soon as that satellite's launched, there's forecasters, eager to use that data, not just able to use that data, but eager to use that data. And so we're working hard, and we have been for several years, to get the data ready for the forecasters. On the top right there, I've shown what a lightning flash looks like from above, and that's at night. So all of you have been in an airplane and you've flown over a sunlit cloud. That's bright. The GLM can see 90% or more of flashes, even within that extremely bright cloud. So it's just a really remarkable piece of technology. And so since we're putting up a GOESR GLM, actually the Europeans are following suit, JAXA's following suit, and the Chinese are actually going to put a lightning imager on their next geostationary satellite. So now kind of it's the world taking the lead from us, and they're doing it a little bit cheaper because we've had to figure out a lot of this technology. But that started some great, hopefully be going over to Italy later this or early next year to work with the Europeans, because they haven't looked at the applications, and that's something that we really focus on. And so going to the next slide, the applications, the GLM mission benefits. Again, I normally would go at length here, but I just want to cover it with one slide. I've shown in the top right the lightning jump. And what you see there is a time series following a storm. So a storm tracks along, and we're tracking time series, seeing how many lightning flashes there are, seeing how tall the storms are, and so on and so forth. But if you look at the yellow line, you see it rapidly increases. It goes almost straight up, and then the blue, black, and green, that's a severe wind, tornado, and severe hail report. And so you had this rapid increase in lightning about 20-25 minutes before you had the severe weather at the surface. And so scientists have actually gone through and quantified that, and now we have a new warning tool. We can look at storms and we can see whether there's been a lightning jump and how significant that was. Lightning will never be used alone to create warnings, but it'll always be used to complement other data. So forecasters, it helps them when they have 4 or 5 storms. They can't focus on all 4 or 5 storms. It kind of helps draw their attention to one or the other. I also put in there the improving satellite precipitation estimates. It's the idea of low Earth orbit. So when we have these flying around quickly, seeing just snapshots at a time, they can have radar, so they can see very detailed where the heaviest rain is and where the light rain is. But when you're in geostationary orbit, they only have infrared sensors. And so clouds will get cold enough that basically they're just seeing how cold the cloud top is. And so you'll get a huge storm that's all the same temperature. But really, it's underneath it, there's different stuff going on. And so what the lightning data tells you is where the heaviest rain is. And so underneath that cold cloud shield that's uniform, that's hard to pick anything out of, you can say, okay, where there's lightning and a lot of lightning, there's heavy rain. Where there isn't lightning, there probably isn't heavy rain. And so that's one of the that's you need the uniformity of the GLM to be able to provide that type of added value. And then on the bottom right there, I put, it's hard to see even for me up close to it, but basically the NLDN, or in this case the GLD 360, provides lat-long locations. It tells you pluses and minuses of where the flashes were. Now, when a forecaster's looking at that and they get lots and lots of pluses and minuses, it just turns red, right? They can't tell a relative value. And so what we did with the Ocean Prediction Center is we went in and we gridded this up, and we decided now we'll just make a color scale. Now it looks like radar. Where you have lots and lots of lightning, it's red. Where you have less lightning, it's a lighter color. And so the forecasters with the Ocean Prediction Center who are out over the ocean, they've never had a radar before. They had to wait for these overpasses once or twice or 3 times a day. Now they can continuously watch underneath that storm, or underneath those clouds, and see what's going on with the storms. And so we've seen meteorological things that we see over the US all the time that we weren't sure occurred over the ocean. Now we can actually see they are occurring over the ocean. So it's really exciting. And sitting with forecasters, that's another thing I do. I'll sit with the forecasters and watch how they use this to try to make it better. So it's kind of a back and forth there. And then let's go to the next slide. This goes into the super rapid scan. So currently when you see a visible satellite image, this is where we'll probably have to like get up and have group participation. Go ahead and click play on the video if you could. And what this is super rapid scan. Right now when you see a satellite image, it only updates every 15 minutes. In the GOESR era, it'll be every 1 minute. And so it's just amazing what you can see, these storms bubbling up. And as you get later in the day, you can see more definition. That's because the sun's getting lower in the sky and it's casting shadows within the clouds. The turrets are casting shadows. We could play it again, I guess. If it doesn't, you have to play it a second time. And on the left there is just what the lightning mapping array sees. It shows that there's that much lightning throughout the whole day. But we're really excited about this spatial resolution, or this temporal resolution. It's just really remarkable that we're going to be able to see this type of stuff. And now, if you go to the very next slide, this one will play by itself and it'll continue to play. I'm very, very proud of this one because this is my vision of how the GOESR will be used. My thought is that you will have this when you turn on channel 4 and watch the weather at the end of the day. You'll have something like this. Basically what we took was super rapid scan, which they do for 2 months a year because they don't want to burn up the satellite that's in orbit. It's a spare. They do it for 2 months a year, and we get this phenomenal data. We took that, and based on the LMA, the lightning mapping array, we just changed the brightness of the pixels. Nothing too complicated. If you're trying to show the general public, you don't need a bunch of bright colors. This is pretty obvious, right? And so my gimmicky name for it was shuttle view lightning, right? This is what you would see if you were up in space looking down. And so as it loops through again, the red things are tornadoes. And so as it's going along, you'll see a rapid increase in lightning. It gets really, really bright about 20 minutes before that tornado touches down. That's a lightning jump. Both of these storms exhibited lightning jumps on this day. Did everybody see it? Does anybody in the back want to see it? I'll walk it around to you. Everybody's good? Everybody, yeah, it is. But I can show it to you afterwards too. But so this is just something that we decided to do to show kind of what our vision is of the future, how this data can be visualized. And then if you go to the next one, this is where I have a couple slides here. I wanted to focus on what's called the Washington, D.C. Lightning Mapping Array. When I first came to the University of Maryland, I was a postdoc and I was working. My job was to make sure this thing was up and running. And so that took a lot of my time. It's 2003 technology that was installed in 2007, and it's 2013, or it was 2013 when I was trying to get this stuff working, and so it took a lot of time. But anyhow, now I have students to do that, so I send out my minions to take care of that. And with them fixing the sensors, now I can advertise it. Now I can go and do this outreach type stuff, which is what I wanted to do in the first place. So it's kind of a catch-22. You couldn't brag about the network if it wasn't working, but you couldn't keep it working while you were bragging. So luckily now I have both. So what I've shown there on the top right, again, it's a GOESR Proving Ground project. We're getting forecasters ready for the next generation. The tremendous outreach opportunities, the teaching tool. That's what I use it for most. It's a teaching tool. And so we've collaborated with the Capital Weather Gang. I don't know if any of you have heard of the Capital Weather Gang. So we collaborated with their photographer, and what I've shown in the bottom right there is a little matchup. So he took a picture of lightning, and it just looked like a huge flash with the Washington Monument there. And I went and grabbed the LMA data, and it shows that this, what looks like a huge lightning flash in this picture, is such a small part of a much larger flash. It's a huge flash. It goes up to Rockville. And so there's a couple of AP reporters who caught on to this, and I'm nearly certain these lightning strikes we've been seeing, some are way bigger than they even seem. That's the exact message I was trying to get across. And so that was an AP reporter. And then the next guy said, a flash of lightning weather geekiness, yet cool. And so that's a badge of honor for a scientist, right? I just got called a geek. And then there was another guy that said, the Capital Weather Gang has ascended into a new realm of geekery with this mind-blowing dissection of lightning. So there's a lot of geeks being thrown around, but it was cool. A lot of people really liked it. And so then if you go to the next slide, that's what I did this summer. So Kevin was right down here at the Thomas Jefferson Memorial, and he took a picture north looking at the monument. And in that picture, he captured a lightning flash that he wanted to call a bolt from the blue because it was probably clear air above, but there's too many clouds in there for me to call it a true bolt from the blue. But the idea is that this flash initiated 10 miles from where it came to ground. It initiated in Falls Church at about 35,000 feet, and it hit ground in Silver Spring, and where it wasn't raining, and where the threat might not be obvious. They probably hear some thunder, but if you go to the next slide, everything else is too hard to see, and then this one you'll have to play as well. I went through and very tediously connected the dots to make this, and so we'll play it twice. But the first time through, it just shows you this is how big a typical lightning flash is. There's nothing extraordinary about this lightning flash. It's fairly standard, and so basically you're seeing it started in that cluster south over Falls Church. It traveled both up and down at the same time, which is what most lightning flashes do after the breakdown. And the one channel just decided to come and hit ground at an apartment building in Silver Spring. There's no rhyme or reason. We'll never predict it. There's no lightning network that's dense enough to do that. So, but basically, that's what we're trying to use to teach the public how impactful and how big these lightning flashes can be. And then finally, I'll go to my last two slides. These are Rocky Mountain National Park, 11 July 2014. Is that where everybody's at? Unfortunately, there was the first lightning fatalities in Rocky Mountain National Park in over a decade. And it's a very unfortunate event. It killed a hiker and injured 7. And if you look at the top picture there, that's looking out at the trailhead, the Ute trailhead. And just about at the end of that, so 100 or 200 meters ahead of you is where they were hit. And there's cars in that picture. So there were cars nearby. They could have gotten back to the cars. What you see there that it pains me. We were hearing claps of thunder everywhere, but there wasn't any lightning. And that's kind of the problem. People don't always associate thunder and lightning, but if there's thunder, there's lightning. So the problem in this case is that they couldn't see the lightning. It was behind a mountain, so the second picture down is actually looking west from their position, and Sundance Mountain was in the way. And so they were hearing the thunder from a storm, but they couldn't see it. And so this just shows you when people Rocky Mountain National Park is terrific because it provides you access to areas you couldn't get unless you were a mountain goat. And people can drive up there now, but they're not from there. They're not familiar with the risk. They don't know what time of day and what time of the year these storms come. And so it makes it very, very dangerous. The other thing is that the mountains, the thunder reverberates differently in the mountains. So you may be hearing thunder over there, but the lightning's actually over there. It's just the way that the canyons and the mountains direct the sound. On the bottom left, I've shown it's a time series plot. The blue is intracloud lightning flashes. You can see it starts at about 10 kilometers away, maybe an hour beforehand, and it gets closer and closer and closer, and then boom, it's right on top of them. And so they were hearing thunder, but the cloud-to-ground flash, the one that killed them was the first one. And that's the way it almost always is. Once the threat is obvious and there's cloud-to-ground lightning everywhere, people get to safety. It's that early in the storm that we have trouble with. And the bottom right panel I've shown, this is from Vizsla, the NLDN, and it shows that there was 3 ground termination points. And so in the mountains, you're more likely when a flash does occur that it terminates at separate areas. It hits 3 or 4 different spots at the same time. And that's likely what happened in this case, was that it hit a couple different peaks at the same time. This event was extremely tragic, and the only thing that made it more tragic, if you go to the next slide, is that the very next day, less than 5 miles away, another person was killed by lightning. So unfortunately, the Rainbow Curve parking area, there was folks there, and there was lightning along a distant ridge. In the bottom right image, you can see there's a distant ridge down to the southwest where there was lightning occurring. It wasn't that lightning that eventually hit. It was a new storm that formed to the north of them, and a flash came out of the side of that storm as it tracked by. And so that's probably closer to a bolt from the blue than the other one I showed. So it was just incredible that this could happen 2 days in a row. Fortunately, nothing's happened since, and these are 2 of the 26 this year. If you go to the next slide now, this is just the animations of the case. And so for the north case, what you had is that storms existing, and then when these storms, they produce rain that produces gust fronts. So you felt the cold air come through in front of the rain. That often will trigger a new thunderstorm, and that's what it did. As this outflow hit the upslope of the Ute Ridge, it produced a thunderstorm, and that thunderstorm wasn't there 10 minutes before. that thunderstorm formed over top of them. And so the idea is that the thunder that you heard isn't from the storm that hit them, it's telling you that the environment is ripe and that thunderstorms can form suddenly like that. In the bottom case, what I've shown, again, down to the southwest, there's existing storms, but the one that hit them formed just north of them 20 minutes earlier, came down, it wasn't even raining where they were hit, and they were struck and killed by lightning. And so it just goes to show, that we still have a lot of work to do. We have these great observation networks, but there's a social science aspect, and the next talk will really hit on all these points. You can go to the summary slide, which is the next one, and I'll just leave that for you. The one thing that I didn't reiterate enough here, I think Amitabh did a very good job of working it into his talk, is the idea that these data sets are complementary and that it's not one or the other. You need both, and there's a lot of reasons why you need both. One specific application I could mention is wildfires. That's one that I'm working on. So the cloud-to-ground network will tell you exactly where a lightning flash hit within maybe 200, 300 meters. It'll tell you the peak current. So we can guess if it's a positive flash, chances are it had some long continuing current, which is the key for starting fires. But unless you're very close, you can't always see the continuing current. And that's the most important fire parameter. And so what we'll do in the future is we'll have a system that tells us what's the likelihood that flash started a fire. And it'll use the NLDN or the ENTLN or any of these ground-based networks to tell you where the flash hit, and it'll use the satellite to tell you how long that flash lasted. Could it have produced long continuing current? And obviously we'll work in data about soil moisture and the vegetation and all that, but it'll be a tool that tells you where do we go investigate? Where's the most likely place that lightning started a fire? The last 2 points there, lightning can travel long distances from the parent storm, and recreational activities often place folks at risk, especially when they're out in Rocky Mountain National Park or some Florida on to Disneyland, somewhere they're not familiar with. And so that's all I have for you. Thanks again for your attention.